Let us shift to various cycles, feed systems, thrust chambers for large propulsion systems. One key point I want to make to you is the following. Rocket operating conditions are always at high pressure, but the question is what pressure is good and what pressure is not good. In comparison to solid rockets, the liquid rockets have a certain advantage. In solid rockets, the propellants are carried in the chamber and the entire chamber has to be pressurized. In the case of liquid rockets, it is not so. The combustion chamber of the rocket engine enjoys a pressure which is what you decide for performance, and the feed system which provides the fluids into the combustion chamber can be at lower pressure and introduce a turbo pump which raises the pressure and pumps it into the combustion chamber. Because of that, you have an advantage to reduce the possibility of reducing the weight and the system volume of the thrust chamber is a possibility in the case of liquid rockets. I just showing you here that if you take the chamber at 50 atmosphere, the rocket motor would look like this. At 200 atmosphere, it would look like this. And the largest pressure which is currently deployed is 300 atmosphere. So, you can imagine that the thrust chamber is really very small. You may be looking at a large propulsion system. You can carry liquid in tanks which are 2 meters in diameter, 4 meters long, but the actual operation of combustion and thrust generation occurs in a small volume that you see here. And you see here that there are various options for the way you can manage the whole thing. I will show you 2 of them, all others you can actually do infer. What you see here is a thrust chamber. Into this you have a turbo pump which is the turbine, fuel pump, oxidizer pump, you have a fuel tank, oxidizer tank. Because these pumps operate at high speed, there will be problems of cavitation in the pumps. To prevent cavitation, you must supply them at some pressure. So, you have to have a pressurant at whatever pressure, maybe 300, 400 atmosphere, allow through a regulated process pressure into the tanks of the fuel air oxidizer at couple of atmospheres, 5 to 6 atmospheres. That pressure will deliver the liquids into the pumps to ensure that when these are operating at high speed, no cavitation occurs, and these pumps deliver the fluids at pressures whatever is required here. And if you take a pressure here of 200 atmospheres, you will be looking at pressure at the turbo pump of 500 atmospheres. If you are looking at pressure here of say 300 atmospheres, you may be looking at 700 atmospheres as the pressure of the liquid after the turbo pumps. So, this really operates in very difficult conditions, if I may say so. Then these are delivered in 2. In fact, if you have this thrust chamber like this, you have a high heat flux load coming from the flowing combustion gases. To take care of that, you have to cool this chamber, and to cool this chamber, it is called regenerative cooling. The fuel or oxidizer, depends on the choice, so it is not very clear right away. It passes through this and they deliver it into the combustion chamber. So, this is the normal strategy for one class of propulsion system. Well, and you have other systems here. You have fuel pumps, oxidizer pump. Now, in this case, from the turbine, in this case you are leaving it as an exhaust exactly as you are doing it here. This is another class of systems which are used, and to operate it, in both the cases you need a gas generator. What does it mean? When you have to start the propulsion system, you have to start the turbo pumps. Turbo pumps have to be started through high temperature, high pressure gases, and that is called a gas generator. And this cycle is usually called gas generator cycle. And for that, you have to pump the liquids. Normally by gravity it starts up. Then you have to, or you start up using a solid cartridge, spin the turbine. As this turbine spins, it starts pumping and starts feeding liquids back into the gas generator. Gas generator starts stabilizing, and once it starts stabilizes, the RPM of the turbo pump increases and things like that. So, you have a complex system arrangement here to manage the transition from starting to steady state. Typically, it takes in a large system about 3-4 seconds, in smaller systems about a second. There is one here which you see called stage combustion cycle, in which case nothing is let out from the turbine. All the liquids go through the only combustion chamber, and this means that the operating pressures in many of them inside the feed system will be very high, and the performance actually delivered in terms of specific impulse from the stage combustion cycle is the highest of all these options. And insofar as the gas generator is concerned, there are very variety of ways of doing that. You may use impinging injectors, you may use other classes of injectors, mix them. Sometimes to maintain the temperature required for the turbine, which may not be too large, you also add water, as it happens in Vikas engine, and in some other systems you have other variants. I just want to show you the large propulsion system called the Vikas engine, which is actually being deployed in ISRO. It is an interesting combustion system. You have oxidizer, fuel coming in. You have 6 injectors, as you will see here, impinging injectors. Radially, they are coming into the combustion chamber. Combustion occurs here. This incidentally is not a regeneratively cooled system. This original system is not regeneratively cooled, and you have a material called siphon throat, as it is called there. Some equivalent phenolic resin based composite material is used here. It is slightly ablative, not too much for the burn duration that you are looking for. And well, you will see the actual system. You have turbo pump assembly here, and well, the point to notice is this becomes really red hot when actually, if you see the system operating, this becomes red hot and radiates into the space, which is taken at 0 Kelvin. And you have containers for propellant tanks here, and the liquid is stored here. Gas pressure comes here. In the allayed space here, the gas is delivered here to apply pressure on the liquids, which will be drawn into the turbo pumps, which are located here. In this particular system, they need water as well. As I told you, in the turbo pump, you need to spray water to cool it down to temperature required for operation of the turbine, and not true in every case, but in this case it is so. And inside the combustion chamber, you have some interesting feature you see here. The fuel is injected near the wall in a fine spray. This is true for almost every liquid engine, and this keeps the wall cool, okay, so that the heat flux which comes from the hot gases is taken care of in terms of the intensity or ferocity at which it attacks the wall. The liquid actually vaporizes somewhere near about the throat as well, in the way it is designed. Typically about 15% of the fuel goes into this operation. Its contribution to performance is not very significant, and the reason is the following. Inside the combustion chamber, the fuel and oxidizer are delivered, and they move along after impingement, in this case, along the axis. There is an oxidizer to fuel distribution across. Now, near the wall is always fuel rich. So, when you look at the streams coming out of the nozzle, this portion which comes out with a low temperature exhaust, and hot exhaust comes from the other regions. So, when you evaluate the performance, you have to take the total momentum that comes out of this m dot into UV, but different streams have different velocities, temperatures. So, you must take that into account. When you account for that, you will discover that this the film coolant is not contributing a whole lot to the performance. So, you must limit the film coolant required. This is a subject of discussion and intensely done during the design. Okay, there is something called anti-slosh baffle here. The liquids, when they are flying, you will find that they can be dancing inside. They want to prevent that because it may have specific frequency which will affect the performance of the vehicle itself. You also have something called pogo corrector. This you will see is a coupling between all these may be considered rigid or may be flexible depending on the stresses which are applied. it turns out that you must treat them as flexible elements. And if you do not design this pogo corrector properly, you will discover on occasions that there are pressure fluctuations of low frequency which get coupled to the structural system, and this becomes amplified and the whole vehicle can get into difficulty. It does not happen with this vehicle anytime, because the pogo corrector has been designed properly. In the early part of development, Saturn vehicle, it had some difficulties, and they applied their mind to how to overcome that. From that point onward, pogo corrector is one of the elements of design. It's a combination of structures but propulsion, a feed system coupled to the thrust chamber. The specific analysis tools which are used to understand pogo and remove it. I am put together here specific details of various classes of engines built by various countries. There is something interesting that you may want to recognize in this. You see already 170 engine, already 180, already 107, these are all Russian engines. These are what you see as SC, stage combustion cycle. As I told you, in stage combustion cycle, all the propellant which are gone into turbine and others, they all go to the main combustion chamber. So, the pressure in the feed system will always be higher than what is happening in the combustion chamber. Well, its specific impulse is the largest, something like 3100 Newton seconds per kg, if you may say so. Chamber pressure 250 bars, you can imagine how large it is. Burn time is 150 seconds, and its thrust is 7.65 million newtons. So, you will discover that Russian engines using locked kerosene. F1 locks RP1, RP1 is rocket propellant fuel, which is also a form of kerosene. Then you have variety of other systems. These are all, some of them are American, RS-227 is American, RD-253 is Russian, and this is essentially a storable hypergolic combination. Viking engine is the earlier version for Vikas. It's a French system, N2O4 and UH25 is a mixture of UDH and N2O4. These are American engine, and you will see that these are all stage combustion cycle, gas generator cycle. That means the gases which are going out of the turbine go out of the exhaust, and they do not enter the main combustion chamber. Therefore, the chamber pressures in these systems will generally be lower. You will see that the gas generator cycles here 6.66 atmospheres, 44 atmospheres, 48 atmospheres. Stage combustion cycle, they want to get the best benefit, compactness and so on, there the combustion pressures are very high. Okay, continued for other vehicles here. You have the J2 engine which has LOX hydrogen, quite a famous engine, went in the Saturn vehicle, and vacuum thrust is 0.8 meganewtons. Very high specific impulse coming out of LOX hydrogen, as you see here. Both these are gas generator cycles. HM7 is a French engine, gas generator cycle, American engine RL10. So, you see the specific impulse values of LOX hydrogen are in the range of 430 plus minus 10, things like that. Chamber pressures in the range of, because these are gas generator cycles, they have pressures of the order of 30 to 40 atmosphere. Varying burn times going up to 1000 seconds. The gas generators, if you look at gas generators and so-called pre-burners is an idea used in the case of stage combustion cycle. You see, this is a French design, SSM is space shuttle main engine going to space shuttle, LE is a French engine, RD is a Russian design and Russian. This is essentially American design. You will see the temperature of the turbine, turbine entry temperatures are typically in this range, 800 plus minus 100 K, pressures typically of this range, and here the oxidizer to fuel ratio is different from what happens in the main combustion chamber. It can be fuel rich, as usually the case, or oxidizer rich, and this is speciality of Russian engines. That is what I have written here. As can be seen, variety of choices have been made for engines built in Russia, USA and France. Russian engines use stage combustion cycle have always used oxygen rich mode for combustion, and all others have used fuel rich mode. The oxidizer rich operation, it allows for sufficient reduction of turbine inlet temperature since larger mass flow of oxidizer is available. Remember, the oxidizer to fuel ratio is in the range of 3 to 4 or 5. This is because air to fuel ratio you had kerosene 15-16. Remove the nitrogen, you will end up with 4 or 5. So, these numbers are consistent whether you are using air breathing engines or rocket engines. And turbine inlet temperatures can be achieved, and you can manage to run the turbine with that, the larger mass flow rates available because of the oxidizer being pushed in. Russians alone seem to have mastered this, even though Americans have been trying. The choice of materials with high temperature oxidizing environment is the key. It is not easy to develop materials which are also oxidizer compatible at high temperatures. Okay. This is not really my statement, it is stated even in American literature. Yeah. Huh? Which one? It can be used, it is used for semi-cryo in the application that they have done, but once you have the ability to do that, depending on the other elements of design, it does not prevent you from using that. The point I am making is whether a specific design which adopts it for LOX hydrogen is a different question. But the basic question is, if you are using oxidizer rich operation, using that as a coolant, and in LOX hydrogen, in the case of LOX hydrogen, you still use, you can use hydrogen as a coolant also, because ultimately you are going to deliver it in the form of a gas, no? Even in the case of the design which is used in ISRO, your hydrogen coming as a gas and it is coming for the coolant channels, and the pre-burner creates products which are oxidizer rich and pushes into the core.
So basically, she is asking for DG cycle, but what we have discussed is for pre-burner cycle, where we will have high oxidizer rich component coming into the main combustion.
Yeah.
So this is the valid statement is valid.
Yeah. Yeah. Now, ultimately, your ability to do one thing or the other is controlled by the fact whether you have material compatible with oxidation at high temperature. And the only point I am making is Russians seem to have mastered the technology, which is otherwise not available. Well, I look at cooling aspects now. I wish to tell you that the subject is so vast, I can only address a few of them, and I will address only select few of them. As I see it as prominent, it is some bias from my side. So, if you have other point to make, you can raise the questions, you can debate them. Cooling is an important element in all such liquid engines, and you can do a simple analysis. You have a choice of ambulative cooling as you saw in gas engine. You can use regeneratively cooled systems as used in other engines of LOX kerosene or LOX hydrogen, and you can use simply a heat sink for short durations or small thrusts as it happens in monopropellant systems. So, it is a function of burn time and the thrust, and short burn times, and you do not have really large thrust anyway with short burn durations. Usually short burn durations have small thrusts, and you can afford not to have anything other than a heat sink. As I told you in the case of the gas engine, the whole thrust chamber becomes red hot and radiates heat. It is okay for 100 seconds or 150 seconds, it is perfectly reasonable to have it. Pressures are not large, that is the reason. And if you go to ablative domain, you have larger temperature range. You can't have too much of higher pressure, because higher pressures mean higher heat fluxes, and it can't stand that. And if pressures are low, you can do radiative cooling as well, as I mentioned to you in gas engine. Larger thrusts and larger burn duration, you have probably no choice but to use regeneratively cooled. In point of fact, the gas engine, There were debates at some point of time whether to convert that into a regeneratively cooled system. So, which means that it is a borderline case between one or the other. If you had done regenerative cooling, you would have gained in terms of performance, because the liquid would have been heated, pumped into the system, so we gain. Okay, it's a matter of design ultimately and choices you make in the development of a system. I just mentioning to you a key point here. If you look at the heat flux inside the combustion chamber, now what I mean is, you go along the axis, hot gases are moving, transferring heat to the surface. Just remember, every liquid engine has film cooling. So, that benefit of vaporizing that liquid is taken advantage of. You will see the heat flux through the thrust chamber is of some value. Near the throat, it goes up to very large values. You may want to ask why. Why does it happen that at the throat you have very high heat fluxes? The flow rate is the same. You are reducing the diameter. Why does it happen? Well, I do not want this to be a discussion session, but I just want to show you the result here. The Nusselt number, which is indicative heat transfer coefficient, is a function of Reynolds number, and the coefficient A is about 0.8. That means Re to the power of 0.8. It shows that the flow is turbulent. That the Nusselt number going like Reynolds number to the power of 0.8 implies that the flow going past the surface is turbulent. That is all it says. So, the Nusselt number behaving with Reynolds number means what is the question. Now, if you see here, Reynolds number is, you can express it in rho u d by mu, or you can say m dot by 4 pi d by mu, and if you follow this, you see that mass flow rate is constant through the whole system, but d changes. D comes down and increases. So, d is the lowest at the throat. That is the reason why the heat flux, which is proportional to Re power 0.8, means d to the power of minus 0.8 will show you that it will be the largest at the throat. This is just the elementary feature that you have to keep in mind. There are few tricky features in the design of cooling systems which actually border on heat transfer, and some of you from mechanical engineering must be aware of this. What you see here is the heat flux coming from the gas, and you have inner wall, and you have a surface with liquid which is flowing here, and you have the ambient condition. So, this you have a heat flux which transfers, there is a temperature which is achieved here in steady state, another temperature achieved in the liquid side, and you have liquid flowing through it, at which temperature is increasing. So, your simple convective heat transfer will just take the heat and move, and it moves off. But you could go to a stage where you begin to nucleate boil, that is, small bubble states start coming out, and they carry much more heat in some way. So, at that the heat transfer, the heat flux which is absorbed from the system goes up substantially, but you can only go up to some stage. If you go up to that, below this stage, you are in good shape. The heat flux that is extracted from what is delivered to it from the combustion chamber is extracted better. And the temperature is not going too high. You see, the liquid temperature changes only very small amount here. But if you are careless, this goes to nucleate boiling, it goes to film boiling, which means a thin film of fluid or stream is passed, and in between the temperature has to be very large, temperature gradient has to be large to extract the heat. So, the wall temperature shoots up dramatically. As you see here, the wall temperature has increased to very high values, and if this happens, it burns up there. So, you have lost your hardware. So, that is why this design is a very critical feature, and to ensure that it happens in regenerative cooling systems, they do many strategies. They introduce the liquid into one place, take it downstream, take it upstream, and introduce additional liquids somewhere. In the case of the engine which is being built in ISRO, also many of these strategies are deployed. That is because the Russian design on which this is based has very similar features.